vector space. And we sort of have in mind that all these things together will generate the algebra A multiplicatively, but we're not going to talk about A anymore, because everything we're going to say about the quantum field theory will be said entirely in terms of these operators OX. So these are meant to be the observables localized at a space. Well, when we have a finite number of distinct points in space-time, we can take an observable at each of them, multiply it together in the algebra A, and apply our expectation that we had before. And that will give us a lot of multilinear maps from products of copies of the individual local observable spaces into the complex numbers. Traditionally, those maps are called the vacuum expectation values of the theory. Now, in the path integral picture, which I began with, those functions are to be thought of in the following way. We had the space of fields, or the space of objects, and the O of x is meant to be the functions of the objects, which only depend on the germ of the object in the immediate neighborhood of the point x. So, you see, if we have, for example, a vector bundle with a connection, say the curvature of the connection at the point would be exactly such a function. The things that we're going to integrate are products of functions like that with respect to the, in fact, impossible measure, which is meant to be on this rather peculiar space. So the question is how to make some sense of that. I felt I had very little understanding anything about quantum field theory until in the 1980s I came in contact with string theorists who explained to me that the central idea of string theory, well, in the 1980s this is the fact that two-dimensional quantum field theories are very much the same thing as Riemannian manifolds. There's a kind of modular space of Riemannian manifolds, or at least certainly of closed Riemannian manifolds of a certain dimension. And correspondingly, they said there's a space of two-dimensional quantum field theories of a certain kind. And the relationship between the manifolds and the theories is that associated to a manifold there is what's called its sigma model, in which a field is just a map from the space-time, two-dimensional space-time, into the manifold. We put some measure on that and make a quantum field theory. Well, the reason string theorists were interested in this was that they wanted to do quantum mechanics on the space of Riemannian manifolds in order to understand gravity quantum mechanically. And the hope of string theory at that time was that the space of two-dimensional quantum field theories was somehow a superior model of the space of Riemannian manifolds. It was somehow better adapted to doing quantum field theory on. That was the hope of string theory at that time. Well, I was amazed to hear this because I had had no idea up to that point that a quantum field theory was something anything like as concrete as a manifold, anything like something which one could form moduli spaces of, or consider the tangent space, the deformation space to. But there were several theorems current at that time, which not only, which elaborated this picture. The first one was the famous thesis of Daniel Friedan, who argued that if one considered the space of Riemannian manifolds with its Ricci flow, the essentially the gradient flow of Einstein's gravitational action for a manifold, then that corresponds to a flow on the space of quantum field theories, which he called the renormalization group flow, but it's actually just the rescaling flow. If you have a quantum field theory, you can certainly rescale all the dimensions, you can rescale all the distances involved in it just by changing the metric of space-time, multiplying the metric of space-time by a constant. And that flow on the space of theories was meant to correspond to a very, very important geometrical, natural flow on the space of Riemannian manifolds. More abstractly, but more mathematically in a sense, there was the Zamolodchikov-C theorem, which said that there was a real valued function defined on all two-dimensional quantum field theories, whose gradient flow was simply, again, the renormalization flow, which rescaled the lengths in space-time. So a picture was beginning to be observed of a great deal of geometry associated at least to two-dimensional quantum field theories. So that made me very eager to try to formalize the properties that were being used in these results, especially of Zamolodchikov, which was very mathematical looking in its presentation. And also, if possible, Friedan's theorem, although as that involved actually constructing a sigma model, and no one claimed to be able to do that, and it looked extremely out of sight, I was less sort of excited by the possibility of trying to make progress with that. Let's go back to the abstract picture of quantum field theory given by the path integral. The most obvious suggestive thing that the path integral gives one is the idea of a factorization property for the vacuum expectation values. Suppose our manifold, our space-time manifold sigma, is divided into two parts by a codimension 1 submanifold S. I'm sorry that I'm using S for the manifold here, it has nothing to do with the action of the theory. And suppose that the finite set of points where we're taking our vacuum expectation values have some of them in sigma 1 and some of them in sigma 2, the two parts into which sigma is divided. Then what happens is that we can associate to the interface S a topological vector space, in fact a pair of topological vector spaces in duality, one derived from thinking of S as the boundary of what's on one side, and the other thinking of it as the boundary of what's on the other side. Well, this vector space we can think of in the path integral picture as the functions on the values of the fields along the interface S. But however we think about it, we can think of it as providing a boundary value for quantum field theory in the one half or in the other half. And we can think of the expectation values of the fields just in one half as given by a function on the boundary values, and therefore a vector in the vector space associated to the interface. And the vacuum expectation value that we started off with should be obtained simply by pairing the two elements of the dual topological vector spaces associated to the configurations in the two parts into which the space-time is divided. So that was a factorization property. I thought about this, and it immediately suggested, at first I suggested it rather as a joke, that there was a cobordism definition of a quantum field theory. Supposing one considered the class, what mathematicians call a d-dimensional cobordism category. This is a category whose objects are d-1 dimensional compact oriented manifolds, pictured here as S0 and S1 in my diagram. A morphism from one of these objects to another is a cobordism, a d-dimensional manifold sigma, whose boundary consists of two separate pieces, one being sigma naught, oriented as an incoming boundary, and the other being S1, oriented as an outgoing boundary. That category was introduced long ago in the 1960s by Milner in the course of proving Smale's H-cobordism theorem. Well, we compose objects in this category simply by concatenating the cobordisms. We string one cobordism along after another if one ends where another in a manifold with which another begins. And the factorization property of amplitudes seems to suggest that what we have is a functor on this category, which assigns to each d-1 dimensional compact oriented manifold the topological vector space, probably a Hilbert space, and to the cobordism an operator u sub sigma from the vector space associated to one end to the vector space associated to the other. Well, now if we're doing quantum field theory, the cobordism sigma should have some kind of metric. At first, I thought in terms of what are called Wick-rotated theories, in which we build a model of the theory in which is adapted for space-times in which we have not a Lorentzian metric as we do on a genuine space-time, but a Riemannian metric. And it seemed that an appropriate axiom was that such a cobordism should be represented by a trace class operator. And for obvious reasons, one wanted this functor to have a simple behavior if you simply put cobordisms side by side. If you put two d-1 dimensional manifolds side by side, the topological vector spaces associated should simply tensor, and the same thing should apply to the morphisms. So that was the cobordism functor definition of a quantum field theory. I'll come back to the question of what kind of metrics the manifold should have in a moment. If the structure I just described was to have any claim to look at all like a quantum field theory, it had to give us some local observables, the things corresponding to the spaces OX we gave in our earlier characterization, and something correspond to their expectation values. But that was very easy to do, because if we take a point X in a space-time sigma, it's surrounded by a decreasing sequence of very small d-1 dimensional spheres defined by the metric of the space-time, which form a system of d-1 dimensional manifolds which are linked by the cobordisms between them, the part of the manifold between one little sphere and another. So for a very small sphere, we should think of the vector space associated with that little sphere as essentially the space of observables at that point. Or to be more precise, we can take the inverse limit under the system of small spheres as the sphere shrinks to a point. We can then think of the manifold sigma with a small hole removed from it, a small disk removed from around each of the points x1 up to xk, distinct points of sigma. And we can think of the resulting space-time with little holes as a cobordism from the boundary of the holes to whatever other boundary it may happen to have. But in particular, we may think of sigma as being a closed manifold, in which case, by the tensoring property, the vector space associated to the empty manifold being the complex numbers, the punctured cobordism will simply give us a map which we can take as the expectation value of our local fields. So we have something like the structure of a quantum field theory. Now, in order to define quantum field theories traditionally, one said they were defined by the expectation values of their local operators. One had to give an enormous number of somewhat unmotivated, certainly to my eye, properties that these expectation values should satisfy. Much the most powerful and coercive of the properties relate to the system having positive energy. And one thing which, not quite at first when I proposed the definition, but actually quite soon after became clear, and led to work which I published jointly with Maxim Kontsevich, who had exactly the same ideas completely independently, was that the phenomenon of positive energy could be very simply included in the cobordism functor definition of quantum field theory simply by equipping the cobordisms with what we call allowable complex metrics. So a complex metric is something analogous to a Riemannian metric, a bilinear form on the tangent space at each point of the space-time, but one which, while remaining real bilinear, is allowed to have complex values. So the length squared of a little interval was a complex number, an infinitesimal interval was a complex number. Well, we wanted that to have some kind of positivity property. And there are many different ways of stating the positivity property, but to me the simplest one is when you have a Riemannian manifold, a good way to encode its metric is in a Dirac operator. Any metric has Clifford modules, vector bundles which are modules for the Clifford algebra of the tangent space at each point. That certainly is just a way of encoding the metric. Once you have Clifford actions on the fibers of the vector bundle, you can define the Dirac operator. And the condition we want is that the Dirac operator, we can do that just as well for a complex metric. The condition we want is that for any one Dirac-style operator formed with the complex metric, the Dirac operator is a contraction operator. So that's a condition on the complex metric. We studied this and we found it was a very attractive definition because it gave a domain of complex metrics which precisely had, which of course contained ordinary Riemannian metrics, and for which the ordinary Euclidean Dirac operator is certainly a contraction operator, but had on its boundary precisely the space of Lorentzian metrics. So we're very like the position we had on an earlier slide when I described the semigroup indexed by half-plane C plus of complex numbers. So let's draw that picture again, where we think of the real axis along which in a quantum system we had the semigroup generated by the positive real numbers. Well, let's put along that positive axis a cobordism functor where the manifolds have Riemannian metrics. But let us also ask for the functor to extend over the whole domain of manifolds with complex metrics in such a way that the associated operator depends holomorphically on the complex metric, and is still the trace class contraction operator everywhere in the whole domain of these cobordisms with allowable complex metrics. On the boundary of that, we'll have a space of cobordisms of manifolds with Lorentzian metrics. And we can hope, and with some simple hypotheses can prove, that a theory of the type I described in terms of the complex metrics will have a unitary boundary value, which is a Lorentzian quantum field theory on the semigroup of cobordisms on the boundary. But they are cobordisms which can go both ways. We have a time direction. A Lorentzian cobordism can have its time direction reversed, and that will have a unitarity property with respect to that reversal in suitable circumstances. There was very little trouble in formalizing this picture, and it had some very attractive features. One of them was that it explained why we do quantum field theory with Lorentzian signature manifolds, but we don't, for instance, ever try to make time two-dimensional. Well, it's only Lorentzian manifolds which form the boundary value of the kind of complex metrics we regarded as allowable. And there was no condition in the allowability which seemed to relate in any way to any possible signature of the boundary value of the domain. The next thing is, of course, we automatically encoded all the positive energy and Wick rotation properties which play a very big role in the usual formalizations of quantum field theory. So these were encoded very, very concisely. Perhaps more surprisingly still, one of the things that simply dropped out of the formalism was that when one went to the unitary theory on the boundary, one still had field operators, just as the field operators extended to field operators in the Lorentzian cobordisms in the boundary. But then we had the property dropped out that field operators which were at points of the Lorentzian space-time on the boundary, which were, as one says, space-like separated, which can't be joined by, that means they can't be joined by any path which travels with the speed of light in the Lorentzian manifold from one to the other. The operators corresponding to such space-like separated operators, observables, must commute. And that local commutivity property is one of the more or less completely unmotivated features of traditional expositions of quantum field theory. So the last thing I want to talk about is why, nevertheless, I felt very disappointed by the picture in many respects. I came into the subject wanting to prove that two-dimensional field theories had a modular space which made them look like the modular space of Riemannian manifolds, or something like that. Could one prove such? I mean, from my point of view, that had been the objective. Well, in fact, absolutely not. The theories, as described, include very, very many things which a traditional quantum field theorist wouldn't think of as quantum field theories at all. For one thing, they're not theories which have any kind of Lagrangian description at all. If they satisfy some of the axioms of quantum field theory, they certainly don't come from any kind of natural path integral interpretation. But much worse than that, they don't have the usual local operators do not include necessarily the local operators that a field theory should have. If we were given a cobordism functor defined field theory, what fields would we naturally expect to have? You expect that any theory has an energy momentum field. That's just the way, that's meant to describe the way the field theory responds to a small change in the metric of space-time. In other words, the field theory gives us certainly a map from the space of metrics on a particular topological space-time, a particular manifold space-time sigma. As we vary the metric, we get a different operator U sub sigma. And we could differentiate that. And that gives us an operator which is a map from the deformations of the metric. We should think of them as some kind of tensor fields on the d-dimensional space-time sigma, which have compact support in the interior of sigma. That's the tangent space, for example, to the space of metrics, of that form. Well, by differentiating, we should get a map from that into operators from the vector space at one end to the vector space at the other, like trace class operators. And that should describe the energy momentum tensor somehow. But is there anything in the corresponding field theory that we've defined with an operator O sigma at each point, which we could somehow smear out over this by integrating it with respect to the tensor density and get an operator? Well, no, there isn't. There's no reason at all why there should be anything in the OX the theory gives us which helps to define that operator at all. Another thing which any quantum field theorist would believe is that if you deform the Lagrangian of the theory, that should give you a deformation of the theory. And much more, any deformation of the theory should be given that way, so that the thing that most importantly the Lagrangian of the theory tells you is the tangent space to the moduli space of theories. The possible deformations of the Lagrangian should be the deformation space of the space of theories. Well, the deformation field would be another field of the same kind, which is associated to the compactly supported smooth tensor field on the cobordism, an operator between the vector spaces at the ends. Well, such a thing are called a Whiteman field. Now, if we could introduce Whiteman fields and show that Whiteman fields were actually somehow the same as the local fields we have, then we would be in a position to start trying to prove the kinds of theorems I originally hoped to prove. Well, recently I've come to believe that one can add to the cobordism definition a scaling property, or a system of scaling properties, which enable one to prove that the Whiteman fields and the cobordism type fields are actually exactly equivalent. So I haven't worked out this theory, so I will just say very roughly what kind of thing it's meant to consist of. You see, we're meant to be able to define that what it's meant to provide is a grading on the, or a filtration by scaling properties on the space of fields at each point x. Inside the space OX, there's the subspace of fields of scaling dimension less than a certain given degree for all possible degrees. How could we do that? The field operator at OX is represented by a field, by an element of the vector space associated to each little sphere around the point X. In order to be able to talk about its scaling, we want to be able to say how these fields grow as the field, as the sphere becomes smaller. In order to be able to do that, you need the spaces associated to the spheres to be somehow roughly comparable. And the way to do that is to say that actually one must be able to define a space of fields of supposedly associated to a sphere at x of dimension 0, which fits together with the actual fields associated to small spheres, so that the whole thing forms a vector space, a topological vector space, on the space of small spheres of all small dimensions, including 0. Well, once one has that, one can of course talk of the degree of a field as the degree with which it tends to infinity as it approaches the fiber at the end of the run. And by I hope that one can build up a theory that will enable us to identify Whiteman fields with cobordism fields.
Please join me in thanking